Hi folks. Today we'll be solving some problems on functions and their graphs at the intermediate level. So let's get started. Find the domain of the following functions. f of x equals x cubed minus 7 over x squared minus 12x plus 20, and g of x equals square root of 7 minus 3x. So we'll begin with finding the domain of the function f of x equals x cubed minus 7 all over x squared minus 12x plus 20. So when looking at that problem, notice that the denominator cannot equal 0. The numerator can range wherever we want it to. It's just the denominator that'll cause problems. So we begin with x squared minus 12x plus 20 does not equal 0. So you can pretend this is just like an equal sign in terms of solving. And an easy way to do this is actually factor. And so this becomes x, the quantity x minus 10 times the quantity x minus 2 does not equal 0. And in order for that to not be equal to 0, that means both factors cannot equal 0. So breaking that into two pieces, you get x minus 10 cannot equal 0 and x minus 2 cannot equal 0. Well, you can, in the first scenario, you just add 10 to both sides. And in the second scenario, you'll add 2 to both sides and you get your answer x cannot equal 10 or 2. And in this case, if we're writing our answer in interval notation, we start with the smallest number, and that would be 2, and we want our interval to go from negative infinity to negative 2, or not negative 2, my apologies, negative infinity to 2, and then we take it from 2 to 10, and then from 10 to infinity. We don't want to include 2 or 10, so we use parentheses instead of the brackets. So you get the domain is negative infinity to 2, union 2 to 10, and then union 10 to infinity, where we're using parentheses on all of those. Okay, now let's find the domain of g of x equals the square root of 7 minus 3x. And in this case, we need the expression underneath the square root to be greater than or equal to 0, because a negative underneath the square root, we're getting a complex numbers. We don't want that for our functions here, at least when we're talking real valued functions. So we need 7 minus 3x to be greater than or equal to 0. Simple step here would be to add 3x to both sides, and once you do that, you get 7 is greater than or equal to 3x. And now just divide both sides by 3, and we do not have to switch the inequality sign since it's a positive number that we're dividing by. So you get 7/3 is greater than or equal to x, or x is less than or equal to 7/3, whichever way you want to read that. And so this means our domain goes from negative infinity to 7/3. And in this case, since we have greater than or equal to on the 7/3 side, or less than or equal to if you go x is less than or equal to 7/3, we want to have a bracket in that case. Okay. So now, determine if the following equation is a function in terms of x. In order to solve this one, even though it looks real scary, we're going to use the vertical line test. So we bring over our vertical line, and then we're going to start scanning from left to right to see if this is hitting at most one point on the curve. Remember, open circles are actually a point that's not included on the graph, whereas a solid dot would mean a point that is included. So notice once we get to x equals 1, all of a sudden we've got a problem. And that problem is we have the points 1, 1, and the point 1, negative 3, both hitting our vertical line. Since there's 2 points hitting our vertical line, that means that this thing has failed the vertical line test. And since it fails, all of a sudden we know it is not a function. Hence, this graph does not represent a function in terms of x. On to our next problem. Determine if the following equation is a function in terms of x. And so we have a graph of our equation here. Now, the key component is our vertical line test. So we take a vertical line starting from the left. We're going to scan it to the right and see if we're hitting more than one point at a time. Notice when we get to negative 2, we'll stop right here just to do a double check. The vertical line is actually only hitting 1 point because that open circle is not included. And so that solid dot, it's only hitting 1 point at that point. And we keep on scanning to the right. 0, when x equals 0, we seem to have another point we got to check. But notice it's only hitting 1 point. It's just that solid dot there at 0, 0. Scanning x equals 1. We've got another just 1 point, so we're good there. And all the points all the way throughout the rest of the curve, it actually is passing the vertical line test. So we have a vertical line is intersecting at most one point. It passes the vertical line test. So what does that mean? That means we do have a function in terms of x. So given this graph, we have a function in terms of x. Now, let's take a look at the graph of the function f of x. Given below, we want to evaluate f of negative 2, f of 0, and f of 1. We'll begin with f of negative 2. So with f of negative 2, we need to take a vertical line where x equals negative 2, and we're going to find where that actually touches the graph. In the graph, it seems like there's that point at that hollow circle, but that actually is not included. The only point that's included is actually the solid dot that appears at negative 2, negative 1. And what we can do is we can cross that over to the y-axis just to double check and make sure that that is negative 1, and in fact it is. So we get f of negative 2 equals negative 1. Moving forward to f of 0, well, when we take the vertical line where x equals 0 and we're finding which point on the graph that it actually hits, well, if you notice, this is a solid dot that appears right in our graph. And so this is the y value here is 0, so we get f of 0 equals 0, and we're good there. Finally, last but not least, f of 1. Well, notice we do the vertical line at x equals 1. We have it intersecting at this point right here, and so this point corresponds to a y value of 1, so f of 1 actually equals 1. So those are our three function values. F of negative 2 equals negative 1, f of 0 equals 0, and f of 1 equals 1. Moving forward, so let's say we have a graph of the function f of x given below, and we want to determine which of the intervals, negative 4, 3, negative 3, 0, 0, 1, 1, 3, and 3, 4, which one of those intervals are where f of x is increasing. So a way we can do this is we can kind of take a dot and kind of follow along the curve, or you can take a line and kind of follow along the curve, whichever you prefer. We'll use a dot here. So we'll start with this blue dot, and as we go, we're trying to see, is our blue dot rising or falling? If it is rising as we move along the curve, that means that we actually have a function that's increasing. And let me state, when we're moving from left to right, just the way we read normally, we're trying to follow the graph along the way. So we're going to begin at this point, negative 4, positive 1, and we're going to move along the curve and just focus on the y value along the way. So with this point, negative 4, positive 1, as we move all the way to when the x value is negative 3, notice this whole time this curve is, this point right here is actually increasing. So for negative 4, negative 3, that whole time we have our function increasing. So we have negative 4, negative 3, it's increasing. Now let's jump to the points negative 3 to 0. So notice from negative 3 to negative 2, we are increasing if you're following that dot. But as soon as we hit negative 2, all of a sudden we start to drop off. And in fact, that is starting to decrease from negative 2 to 0. So that means that interval is not an increasing interval. Okay, let's move to the interval 0, 1. Well, we can start on our dot here and work our way. See, are we rising? And if you notice, we're actually falling with the dot. The dot is going downward. So that means we're decreasing on that whole interval 0 to 1. So that one's completely decreasing, whereas negative 3 to 0 was partially increasing, partially decreasing. 1 to 3, so when we start at 1, notice right out the gate we are decreasing. So that tells us that that interval is not increasing. But last but certainly not least, 3 to 4. So when we start at 3, that's a 3, 2, and maybe a quarter, something like that is our point there. And so when we start from 3 and that point just above 2 at the y, for the y value, if you keep on moving to the right of the graph, notice the dot is actually starting to increase along the way. So that means that this function is increasing on that interval as well. So the intervals of the aforementioned list, we have negative 4, negative 3, and 3, 4 being our only two intervals from that list that actually are increasing. Last but certainly not least, Let's consider this piecewise function. We have f of x equals the absolute value of x plus 4 if x is less than or equal to negative 1, 4 minus x squared if negative 1 is less than x is less than 1, 7 if x equals 1, and negative 5x if x is greater than 1. So we want to evaluate f of negative 6, f of negative 1, f of 0, f of 1, and f of 2. So let's begin with f of negative 6. And if we start with f of a negative 6, we got to figure out which of the 4 conditions listed on the right-hand side that negative 6 is satisfied by. Well, if you notice, negative 6 is less than or equal to negative 1. So that means we're going to plug negative 6 in for the x value in this first equation. So that means we get the absolute value of negative 6 plus 4, which is just absolute value of negative 2, which is the same thing as just 2. Moving on to f of negative 1, when we plug in negative 1, which scenario will we be looking at? Well, if you notice, it's once again that first scenario. Negative 1 is less than or equal to negative 1. So that means all of a sudden, when we plug that in, we should have, and for the x value, we should have negative 1 plus 4, and with the absolute value of that quantity. And so this means we get absolute value of 3, which is just 3. Okay, so far so good. Now we're going to go on to f of 0. Well, we're plugging in 0. Which condition does that satisfy? Notice 0 is not less than or equal to negative 1. So that means it's not the first equation that we're going to plug in for x. However, 0 does fall between negative 1 and positive 1. So that means it is satisfying the second condition, so we're going to plug it into the x in this second equation. So instead of using 4 minus x squared, we're going to plug in 0 for that x. We're going to have 4 minus 0 squared, which is just 4. Okay, so for f of 1, when we look at the 4 different scenarios, which one does that satisfy? Well, 1 is not less than or equal to negative 1, so the first condition's out. 1 does not fall between negative 1 and positive 1. We're looking for something to be equal to, so that even though 1 appears, it's not equal to there. However, 1 does equal 1, so it's that third condition, and notice there's no x value. So what do? Well, we actually have the answer right away. It's just 7. Okay. Last but not least, f of 2. So f of 2, notice 2 is not less than or equal to negative 1. 2 does not fall between negative 1 and 1, and 2 does not equal 1. So those first 3 conditions are all out. Okay. So we're left with that last condition. 2 is greater than 1. So we're going to plug it in for the x in the equation negative 5x. So we get negative 5 times 2, and that means we have an answer of negative 10, and we have all our values to our piecewise function.